In this video, we're going to look at the mean and the median for a continuous random variable. What we're actually going to be looking at is we're going to be trying to find basically the center of the distribution, if you like. Where's the middle? What's your average x value for this particular distribution? And so we'll look at the three measures of center that we normally look at when we're finding measures of center. And that's the mean, the median, and the mode. Now the mode is not actually listed as part of the methods course, but it's one extra thing that's very, very small, and you may as well know it. Why not? So we're going to look at the mean in terms of it being the average weighted value for the variable in the distribution. We're going to be looking at the median as the middle value for the variable in the distribution, so where half of the data is above it and half of the data is below it. And then finally for the mode, it's the same as in Year 8 and Year 9. It's the most frequently observed value for the variable. So let's dive in. So we'll use our definition for mean, median, and mode from our binomial distribution. So our mean is the balancing point of the distribution, the point at which you would place the point on which to balance the whole distribution. So it's a theoretical value, it's an x value here. So the mean is going to be this x value. So the median is the second quantile, or the 50th percentile. So what you're looking for is the area from the lowest value, that should say negative infinity, up until m, that gives the area under the curve equal to a half. You could also come from positive infinity down to m, but that m value will be your median. The mode is the x value for which the function has its maximum value. So for this density curve here, the mode is the x value, so this value here, that sits underneath where the function has its maximum. So this is the function maximum, and that value there is the mode. So in this case, the mode is equal to 0. So don't get tricked into writing the function value maximum. You're actually looking for an x value, that is the mode. So the last thing I want you to do with mean, median, and mode is keeping those things, those ideas in place. Have a go at writing mean, median, and mode for A, B, and C for each of these distributions. Remember, the median is the balancing point. Where would you place a pivot? Where would you place a balancing point? Under A, B, or C? The median is half of the data is to the left and half of the data is to the right, or half of the area is to the left, half of the area is to the right. And the mode is the value underneath, the x value underneath the highest point. And I'll give you a heads up, sometimes one of the letters is more than one of those three things. Press pause, have a go, and then check your answers. How did you go? Mode, always under the highest peak. So A and C are the same height. You might have had one higher than the other. And C as the mode here. The median is your middle point. So for this one in the middle, it's wherever it's symmetric, the point of symmetry here. And if you have a point of symmetry for your two halves, then whatever that x value is will be your median and your mean. Okay, your median and your mean, if it's symmetric, is the middle point. This is symmetric. When you have the skewed graphs, you have to decide B and C, which is the median and which is the mean. And it might be a little bit counterintuitive, but what you actually have, this long tail here and this long tail here, actually drags the balance point back out this way further. So the furthest away from the mode is the mean, so this one is the mean. And for this one, the furthest away from the mode here is the mean, so C is the mean. So let's look at how we actually go about finding the mean. So we've been given a formula that we need to use, that the expected value of x, which is the mean, so the expected value of x, which is the mean, is equal to the integral from negative infinity to infinity of x times by the function that we use to define our probability density function. So what that means is that we need to look at where this function is actually defined. So here's an example. Find the mean of the continuous random variable x, which has a probability density function defined by, and here we have a hybrid function. So from 0 to 1, we're using the x squared function, and we're using 0 as our f of x value everywhere else. So if I just put that straight into the formula as f of x and just used the x squared value, so I used x squared here, I can't go from negative infinity to infinity. I have to be defined by the area that I'm searching, has to be defined by the area for which each segment of the graph is defined. So to find the area of this function, I have the graph of x squared, and everywhere else I have 0. So the only section that has area underneath it is this section of your formula here. So to find the mean of this function, what I'm going to do is I'm actually going to integrate between 1 and 0, or 0 and 1, and multiply our x, just a value of x, times by our function. So let's go ahead and calculate that now. So that's the integral from 0 to 1, x times x squared is x cubed dx. And if we work that out, we end up with a quarter. So similarly, for the continuous random variable x with the probability density function given by this function here, f of x is 2e to the minus 2x, where x is greater than or equal to 0 and 0 elsewhere. If we were to find the mean of this, we need to integrate for this domain. And that means that on our integral, we're going to have an infinity on the top, and that's perfectly fine. The rest of our formula is exactly the same. So we have an x that multiplies the function that we're using for f of x, so 2e to the minus 2x, and we integrate that with respect to x. And if we do that on our calculator, what we get is a half. If you're looking for the infinity symbol on your TI Nspire calculator, it's on the pi button. Just press the pi button and you'll find it. The final section on the mean of a continuous random variables looks at means of functions of continuous random variables. So for example, the expected value of x squared. Now you might have noticed that in the previous few sections I've been colour coding the x here with the x that appeared for the mean over here. So all we're doing with the functions of x is we are replacing the x that was in that integral with matching whatever that function is in here. So here we've got capital X squared, and in our integral we've got x squared. Here we've got e of capital X, which is our continuous random variable, and in our integral we've got e to the little x. So they match, e to the big X, e to the little x. Here we've got sine of capital X, sine of little x. So we would multiply whatever our function was for our discrete random variable by sine of x. So the general formula for this is if you're after the mean of a function of the random variable, and that should in fact be a capital X. Let me just fix that. Should be a capital X. Then you just multiply the function in the integral by whatever that function was that you were finding e of x of. So let's have a look at an example of how this mean of a function of a continuous random variable works. For the probability distribution function defined by f of x, so this function here, find e of, we've got x squared here, so our formula is going to have an x squared in it, and the other one we have is e of e to the x. So let's do part A first. So we're going to integrate between 0 and 2, because we've got 0 and 2 for our section of the function that's defined, and we're going to multiply that by x squared, and then we're going to times that by our function x over 2 dx. We'll do the same thing for e of x, and then work them out from there. So we can either work them out by hand, so the first one will become x cubed on 2 that we're integrating, and the second one will become the integral from 0 to 2 of x times e to the x on 2 dx, and I would probably use my calculator for that one. Anyway, if we work them out, we get 2 for part A and e squared plus 1, all on 2 for part B. Now, you might be thinking, can I just find e of x and do something to it to find the expected value for the probability for the function? So let's have a look at the relationship between e of x and e of a function of x. So let's have a look. Using our previous example, so we've got a probability density function that is x on 2 from 0 to 2 and 0 everywhere else. If we find the expected value for that probability density function, we get a value of 4 over 3. Now previously we found that the expected value of x squared was equal to 2. So how does that 2 relate? Does it relate to this 4 on 3? What about if instead of finding the expected value of x squared, what if we took the expected value, what if we took our expected value, so e of x, and then applied our function to it, which is a squaring function? What would we get if we did that? So what we actually get is we will get the square of 4 on 3, and that is definitely not equal to 2. So we'll get 16 on 9, not equal to 2. Let's have a go at putting our e of x in as our x value into our function for e of x. It's a lot of e's and e's of x's, but anyway, bear with me. So we're going to take the function e, and where the x was, we're going to replace the x, this x up here, we're going to replace that with the expected value of x and see what that gives us. So that gives us e to the power of 4 on 3, And e to the power of 4 on 3 is not equal to e squared plus 1 divided by 2. So what we've just found here is that if we try and take the function, so if we try and take the function of the expected value for a random variable, it is not equal to the expected value of that particular function of the random variable. Except in one case, and we'll get to that later when we talk about linear transformations of expected values. Meanwhile, let's look at the median. To find the median of a continuous random variable, so the median is the middle value when the values are lined up from smallest to largest or largest to smallest. And that's what you get when you put your x values on an x-axis. They're lined up from smallest to largest, or if you like, largest to smallest. So to find the median, what you're looking for is the one in the middle. So we know for a probability density function that our valid x values are the ones where we have area under the curve. So these are our valid x values. So what we're looking for is half of the x values to be below this particular value and half of them to be above that particular value. So it's quite easy to see for the one that I've drawn. We're going to use the area to help us to find it. So this area here is 50% or 0.5. So the area equals 0.5. And on the other side, we have 50% of the data. So that area equals 0.5. And when we're talking about the area for a probability density function, we're talking about the integral. And so to find the median, we'll start from either the lower end to the median value. So from the lower end to the median value. For the function, make it equal to 0.5 and solve. Or you can start with the upper value and put the m down the bottom. Either way, it doesn't matter. So let's have a look at an example about how you get asked these sorts of questions and some of the tricky things to look for. So let's find the median for the probability density function defined by f of x is equal to negative 2x plus 2 between 0 and 1 and 0 elsewhere. So we'll set up our integral using our bounds that we've got here. So our lower bound is 0, and so our integral is going to be from 0 to m. And our function is minus 2x plus 2 dx. We're going to make it equal to a half, and we're going to solve that using our CAS. And when we solve that using our CAS, we get two values for m. We get m is equal to these two values there. So if I turn those into, let me just make this a little bit smaller so we can fit it in. If I write those as decimals, it becomes easier to compare the size. Now, we need to remember that our m is our median, and it is actually one of our x values. And so what we need to have is we need to have our m value fit within this domain, which means that our actual median is this value, because this one is outside of the defined domain. So what it's actually saying is up on the picture up here, our 0.29 would be represented here with half of the area below it and half of the area above it. This 1.7 doesn't fit in this domain, it fits in the elsewhere section, which puts our median up here where there's no area. And it's not possible for this x value to be having half of the area above it and half of the area below it. And what's actually happening is this function continues theoretically down this way, and so you'll end up with a positive area on the top and a negative area on the bottom, and this is how you're getting that other x value over here. But because our domain is restricted to here, we're only leaving one. Now, I've tried this multiple times on the CAS calculator, restricting, so doing a solve function for this and restricting the domain given 0 is less than or equal to x is less than or equal to 1. That doesn't work. The only way to get it to work is to give a restriction here that your m has to fit between these two values. So that brings us to the end of the information about the mean and the median of a continuous random variable. Have a go at the questions in the exercise. Remember, if you are trying to find your median, that you need to be using the domain, but not with the x, but restricting for m on your CAS. Good luck.